In the previous session, we covered vectors and how to add and multiply vectors. We want to move on to the main topic of this section, which is mechanics and motion. But before we do that, we should have a quick look at some very basic calculus, namely differentiation. Now, calculus is often portrayed as something that is really hard, but I hope that in this video I will demonstrate that it really isn't that scary, and actually during your previous maths training you will have secretly been doing it all along, but just in a limited case. So we are going to start with a simple problem that you probably already have done to death. And we are going to be finding the slope of a straight line. So here we have a straight line, and there are 2 points on this line which have the coordinates p1, which is 1 and 2, and p2, which has coordinates 3 and 6. Now to find the slope, we denote that with letter m. We just divide the change in y by the change in x, and in this case that is just 6 minus 2 divided by 3 minus 1, and that is equal to 2. But that's all well and good, and we know that this works as long as the line is straight. But is there perhaps a way to generalize it so it works for any equation? Well, when we start generalizing, we first need to get rid of any specific values. So we get rid of these 3s and 6 and all these coordinates, and we replace them with p1 having coordinates of x1 and y1, and p2 then has coordinates of x2 and y2. And next we get rid of any specific equation, so we say that y is equal to some function of x. And this is a bit of notation that you may not be familiar with. But all this is saying is that there's an equation which takes some independent variable and that spits out your dependent variable. So in terms of this equation, what is y2? Well, y2 is just that function evaluated at x2. And then y1 is just equal to that function evaluated at x1. But then let's have a think about what x2 really is. Well, x2 is equal to x1 plus the change in x, or delta x. And this then allows us to get rid of these little subscripts, so we can write x1 as equal to, well, just x. And then it follows that x2 is going to be equal to x plus the change in x. And we can go back up and we can say that y1 is then equal to f evaluated at x. And y2 is equal to f evaluated at x plus delta x. So if we take the equation at the top, we get rid of those specific values. And we just say that this is, well, y2 minus y1 divided by, well, x2 minus x1. But then we write it in the terms that we have outlined here. So we get f of x plus the change in x minus f of x divided by x plus delta x minus x, and we get that cancels out. So now we have a nice equation. Great, but this still assumes a straight line. What if we are dealing with another equation which is not a straight line? Something like this. Now we can take 2 points along this and plug that into our expression, but that only gives us the average slope over that distance. Now this may have its uses, but those uses would be very limited. But what if we could just find the slope for that region? Well, if we zoom in, we still have the same problem. That's a bit curvy. But if we look at a really small region like that, then eventually we will find that distance becomes a straight line, or it approaches a straight line. So then, performing this operation will become valid. And this is a very important idea, and that is if your change in x is sufficiently small, your equation will follow a straight line over that change in x. And in this case, instead of using the little delta symbol to represent a change, we actually use a lowercase d. So instead of delta x, we use dx, and this represents an infinitely small change, and this is also known as a differential. And then when you take our expression delta y over delta x, we can rewrite that as dy by dx. And we call this the derivative of y with respect to x. So let's go back and take this equation, but rewrite that in our new terms of dx and dy. So we get that dy by dx is equal to f of x plus dx minus f of x divided by dx. And this is the formula for differentiation. And in a practice session for this video, we are going to look at some examples of where we apply this.